OK, so very long instruction words processors still want to have high performance. And we took all this hardware that was in a out-of-order superscalar, and we sort of threw it out. Well, something's got to make up for it. And what makes up for it is a very, very, very smart compiler. So we put a lot of emphasis on the compiler in these sorts of architectures. And the compiler really has to do the scheduling. It has to do all of the dependency checking. It probably has to avoid all the different data hazards. And this is just sort of just getting started. We're going to talk mostly next lecture about all of the different optimizations that a compiler can do to try to approximate what a out-of-order superscalar can do, but by doing it statically. So it's a pretty cool trick. If you take all that hardware, you put it in the compiler, you run it once, and then every time you go to execute the code, you don't have to go and recalculate all the dependencies. Sounds good. OK, so let's see how we execute some code here, and what is the sort of performance aspects to executing loop code on a very long instruction word processor. So here we have a very basic array increment. We're going to take every element of this array. We're going to increment it by the value c. We run it through our compiler, and here's a sequential code sequence. This has not been scheduled yet for VLIWs, or for our VLIW architecture over here. So we load the value. We increment our counters. We actually do the floating point add. We store the value back. We increment the array index, and then we loop. Seems simple enough. Let's see how this gets scheduled here. Well, because the architecture and because the compiler knows about the latencies here, let's say this load here has a few cycles of latency. So it's going to actually schedule this add later. And the add, it's a floating point add. This has a couple cycles of latency also. So it schedules the consumer of that result here, this F2, later. And I don't know, it can sprinkle in the array additions and the counter additions kind of somewhere free. It has lots of open slots. But let's say it schedules it at the same time as the load and the store. So this is pretty cool. We are actually executing two-wide parallelism here. And we didn't need all the extra overhead of in-order superscalar. Oh, and we can even schedule the branch somewhere. OK, so first question here. How many floating point operations are we doing per cycle? Are we doing very well here? This looks pretty poor. We have one floating point operation here, just this add. And we have 1, 2, 3, 4, 5, 6, 7, 8 cycles. Yeah. So we're having 0.18 or 0.125 floating point operations per cycle. It's not that great. We do have some parallelism. We're executing 3 instructions here. It's better than nothing, but we're not really using the machine very well. Our out-of-order superscalar would probably try to take instructions that are below here, maybe intermix them, try to reorder a bunch of things, and try to run faster. So what's a technique to go faster? Well, one of the big as I said, we have a lot of emphasis on compilers in this unit. One of the things the compiler can do is it can actually unroll the loop. So here we have our loop. We unroll it 4 times. And now we're going to sort of take the loop overhead, and we're going to factor it out such that it only happens once every 4 times. Ooh, that sounds good. We're probably going to do some more work here per each iteration in the loop. But things get a little more complicated. What happens here if n, big uppercase N here, our terminating value, is not a multiple of 4? Well, we need to do something about that. We probably need to check sort of before we go to execute here whether we're doing OK, or whether we actually are a multiple of 4. Conveniently, if n is big enough, we probably can run as a multiple of 4 for a long period of time, and it's only the last iteration that we have to clean up. But we need to generate some cleanup code, and the compiler is responsible to do this. So these compiler optimizations do take some effort. OK, so let's look at the scheduling now of our loop unrolled code. We can do a bunch of loads up front here. So we've intermingled these loops. And what's kind of cool is we can actually pull out the loads and sort of throw them to the top, and the stores and push them to the bottom, and then put all the adds sort of in the middle, and maybe sprinkle the array updates somewhere else. And when we go to actually schedule that, we're going to do something similar. We're going to have the loads executing first, execute the floating point adds, have the floating point stores, and have the result. But what you can notice here is we're actually starting to get some overlap. Because we've unrolled, we can overlap this load and the first floating point addition, because we've effectively covered the latency of our functional units by putting other loop iterations during that time. So if you look at this schedule versus the schedule back here, we've just sort of taken these dead cycles and we've put the other loop iterations in those dead cycles. In this loop unrolled case, we're incrementing these counters and the indexes not by 4 anymore. We're incrementing by however many times we've loop unrolled times the offset. So we're incrementing it by 16 now. Does that make sense? Because in this code here, we were incrementing R2 by 4, because that's the size of a single value is 4 bytes. So we have to sort of move our array index over by 4. But now, because we're batching up all this work together, we actually have to move the index by a bigger value. So we're moving it by 4, because we've unrolled 4 times the size of the data value, which was 4. So we're moving it by 16. And one of the nice things here, if you look, is in both the loads and the stores, we're using our register indirect addressing mode here to add in some offset. So we're actually offsetting, let's say, 12 plus this base register of R1 to figure out where we're actually doing the load from. But it's just sort of a convenient way that we don't have to compute a bunch of addresses. OK, so going back here, we can see we're starting to overlap actual operations with other loop iterations. Well, that's really cool. So we're starting to get some performance here. So let's look at the performance. So we'll ask the same question here. How many floating point operations per cycle? Well, hopefully it's higher. 1, 2, 3, 4. Divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cycles. OK, so that's 0.36 is a lot better than 0.125. So this is good. Loop unrolling is helping us. But is this everything, or can we do more in our compiler? So the smart compiler people came up with even a fancier idea, which is called software pipelining. So it uses a term we've seen before, pipelining, but does it in software. So the idea here is that instead of just having one loop, unrolling the loop, and then overlapping the iterations, we're actually going to take multiple of these schedules and interleave them, and try to fill some of these empty slots. So let's look at this. We're going to have the code unrolled 4 times. This is the same piece of code we had on the previous slide. And we're going to draw our schedule that we had before. So here's the schedule we had before in purple. Okay, that doesn't look so bad. But now we're going to schedule it with another iteration of the exact same 4-time unrolled loop, shown here in green. So we've just overlapped this with this other iteration of the loop. Well, are we done here? Well, not quite. We still have some open slots here. So let's try to overlap even another iteration, as shown here in red. Now, the fix-up code that you need to have to do this correctly gets more complex, because all of a sudden now you're basically overlapping multiple iterations. But as long as you don't modify some value, as long as you don't do a store speculatively or a store, you're probably OK, because otherwise you're just doing loads. You're doing extra loads, doing extra work. You're doing extra work, and you're filling slots thinking that you're not going to have anything go wrong, or thinking that the index variable n, if you will, is multiple of 4 and large, and you're not at the end. So let's put some names to these things. So we call the beginning here the run-up, the prologue. Here we actually have our sort of actual iteration. You can see that the, sorry, this is in green. That doesn't show up very well. There are instructions here. There's adds. It's pretty full. We're actually doing a lot of work on our VLIW machine here. And then the epilogue here is when we're done. This is when we're falling out. We're sort of at the last loop iteration of the outer loop, if you will. So let's do some math and look at the performance of this. OK, so that's the same question here. How many floating point operations per cycle? Well, we go look over here. We have 1, 2, 3, 4. And we have 4 cycles in our tight loop case. That looks pretty good. That's cool. We just got a bunch of performance. But we had to do a lot of compiler optimization to make this work. But we were able to use the parallels in the machine, and we were able to overlap 3 different iterations of this loop that we also did a software transform to unroll it 4 times. So this is called software pipelining. And I have a nice picture here to sort of show what's going on visually. So we're going to have time on the horizontal axis, and we'll have sort of activity of how many instructions are executing or something like that on the vertical axis, or shown here as performance. When you run multiple loop unrolled iterations, you have sort of some startup, you have the actual, you're running the loop, and then you come down from that. And that's better than having a lot of startup and sort of come down with a very small loop iteration portion here in the middle. But when we go to look at software pipelined, we can overlap basically one iteration of loops execution with, or one loop's startup or with the loop iteration of another loop. And we can actually execute sort of our prologue, execute multiple iterations, very tight, and then have our epilogue here. Yeah, so our software pipelining, we're only paying the startup and wind down costs once for the execution of a loop and not every iteration of the loop. So that's fun. That's cool. We're getting performance. If only the world was dense loops, life would be easy. Alas, the world is not all loops. If we just had a processor which just did dense array calculations, and all of our problems in the world were just dense array computations, life would be really easy. But they're not. A lot of times code has lots of branches. It has if-then-else clauses. And here we sort of graphically show something like a if-then-else. So we have some piece of code, it makes a decision. It either executes the code on the left or executes the code on the right based on an if statement. So this is the if true statement, and this is the else clause. And data-dependent branches are a problem typically for very long instruction word processors. Now, why is that? Well, in an out-of-order processor, you can try to execute code sort of around the branches and move instructions above the branch and below the branch. But if you're doing static scheduling, when you hit this branch, and let's say it's a hard-to-predict branch, you can't really do anything because you've packed a bunch of instructions next to each other, and they need to execute atomically. So it's not like you can sort of move code up and down across that branch. The superscaler can do that because it has this instruction window, it has a bunch of techniques, a bunch of hardware to be able to do that. But in our VLIW processor, that's a problem. So I wanted to introduce a compiler, an important compiler nomenclature here, which is important for this class. It's called a basic block. So what is a basic block? A basic block is a piece of code which has single entry and single exit. So this is a basic block. It has one entry and one exit. And why is single entry important? Well, if you can jump into the middle of this piece of code, the compiler cannot necessarily reorder the instructions inside this block. And if you have multiple exits, and say you exit here, the compiler can't push instructions below that exit point. But if you have a basic block, the compiler basically knows that this instruction sequence is going to execute effectively atomic, but not actually atomic. I mean, you can have other things going on inside there, but from a compiler perspective, it can reorder the instructions around in here to get better performance. Okay. So loops are easy. We can solve for pipeline. We can unroll. Squirrely code, if then else, spaghetti code, a lot harder. So the compiler guys came up with some fancy tricks to make VLIWs work better and to take advantage of some of the code motion that a out-of-order superscaler does, but in the compiler and not in dynamically in hardware. And one of the more famous ways to do this is something called trace scheduling, which was John Ellis's, who was one of Josh Fisher's students' thesis work. And this was in the Bulldog compiler out at Yale. So what you do is you profile the code. And you come up with the probabilities that these branches go the one way or the other way. So when I say profiling, this is not something that the hardware is doing at runtime. This is something that you do with the program while you're sort of still back in the compiler stage. You take the program, the compiler goes and runs it on some a given input set, and comes up with probabilities of which way things go. And then what you do is you take this profile information, and you come up with some guess at what is the most probable one. And we're going to circle that here and say these darkened edges are the most probable sort of path through this squirrely piece of code, given this is the entry point. Now, this doesn't mean that you can't have branches that sort of branch out of this. But if you do, you need to have some fix-up code. Because what we're about to do is we're going to take this entire sort of big swath of code here. We're going to remove all of the branches. And we're going to schedule for our VLIW processor as one big monolithic piece of chunk of code. And by doing this, we can move instructions, let's say, that are down here, which there's open slots to execute in the early portion of this code sequence. We can move them up. And likewise, we can move things that use the result of long latency instructions up here and push it down across branches. So our out-of-order superscaler does this with branch speculation, but our compiler can do this on our VLIW processor using trace scheduling. But when we do this, we have to be careful Because there's always the possibility that, while unlikely, you can still branch the other way. So typically, the way this is done is you have some form of fix-up code that if you branch away, you have to sort of fix up anything that was after the branch that made a committed change, if you will, to the processor state. You need to sort of roll that back somehow. So we're basically in software doing the rollback case from our out-of-order superscalar. So instead of taking the architectural register file and copying it to the physical register file on branch mispredict, instead our compiler generates a code sequence which does that same operation if you were to branch away here. And we'll roll back only the certain registers that need to be rolled back and only the memory state that needs to be rolled back. So that's pretty cool, is that we can basically take a lot of the functionality that was done in our out-of-order superscalar and put it into software using trace scheduling.